Hello students, welcome to the lecture on probability and probability distribution, and after this lecture we will be able to learn the following objectives. Define probability, describe the probability distribution, understand conditional probability and Bayes' theorem. Let us start with the introduction of probability and probability distribution. Probability theory deals with situation in which there is an element of randomness or chance. The mathematical theory of probability arose in consideration of games of chance but is now widely used in far more practical and applied situations. A random phenomenon is a situation in which we know what outcomes could happen, but we do not know which particular outcome will happen. For any random phenomenon, each atom or trial generates an outcome. Something happens on each trial, and we call whatever happens the outcome. Experiment is a process of observation that leads to a single outcome that cannot be predicted with certainty.
The concept of probability is similar to the idea of percentage. You hear people every day say things like something has a 50% chance. The difference is that in probabilities, we will not say that something has a 50% chance. We will say that the probability is 0.5. So, first of all, probabilities are numbers between 0 and 1. If an event has a probability of 0, that is an impossible event. And if an event has a probability of 1, then we will call it a sure event. Not only that, the sum of all the probabilities in any particular situation is 1. What we mean is this. Let me give you a little example. Let's say that when a child is born, the probability that the child will be a girl is 0.6. So what is the probability that the child will be a boy? It has to be 0.4 because the total has to be 1, which in percentages language we would say 100%. So keep these two ideas in mind. Probabilities are numbers between 0 and 1, and the sum of all the probabilities in a particular situation.
Probability of a single event. Event if we roll a 6-sided die. There are 6 possible outcomes and each of these outcomes is equally likely. A 6 is as likely to come up as a 3 and likewise for the other 4 sides of the die. What then is the probability that a 1 will come up? Since there are 6 possible outcomes, the probability is 1 by 6. What is the probability that either a 1 or a 6 will come up? The two outcomes about which we are concerned are called favorable outcomes. We can compute the probability of a 1 or a 6 using the formula which is as shown on the screen. Let us understand the meaning of probability. Probability is the branch of mathematics that studies the possible outcomes of given events together with the outcomes' relative likelihoods and distribution. The analysis of events governed by probability is called statistics. There are several competing interpretations of the actual meaning of probabilities. Frequentists view probability simply as a measure of the frequency of outcomes, while Bayesians treat probability more subjectively as a statistical procedure that endeavors to estimate parameters of an underlying distribution based on the observed distribution. A properly normalized function that assigns a probability density to each possible outcome within some interval is called a probability density function, and its cumulative value is called a distribution function. A variate is defined as a set of all random variables that obey a given probabilistic law. It is common practice to denote a variate with a capital letter. The set of all values that x can take is then called the range, denoted R subscript x. specific elements in the range of X are called quantizers and denoted X, and the probability that a variate X assumes the element X is denoted as shown on the screen. Probabilities are defined to obey certain assumptions called the probability axioms. Let a sample space contain the union of all possible events E subscript I, so S is as shown on the screen. Let E and F denote subsets of S. Further, let F dash not equal to F be the complement of F. Look at the screen to understand this.
If you roll a fair six-sided die, there are 6 possible outcomes, and each of these outcomes is equally likely. A 6 is as likely to come up as a 3, and the same goes for the other 4 sides of the die. So what is the probability that a 1 will come up? Since there are 6 possible outcomes, the probability is 1/6. What is the probability that either a 1 or a 6 will come up? The 2 outcomes about which we are concerned, a 1 or a 6 coming up, are called favorable outcomes. Given that all outcomes are equally likely, we can compute the probability of a 1 or a 6 by dividing the number of favorable outcomes, 2 in this case, by the total number of possible outcomes, 6 in this case. So the probability of throwing either a 1 or a 6 is 1/3. Don't be misled by our use of the term favorable, by the way. You should understand it to mean favorable to the event in question happening. That event might not be favorable to your well-being. This formula applies to many games of chance. For example, what is the probability that a card drawn at random from a deck of playing cards will be an ace? Since the deck has 4 aces, there are 4 favorable outcomes. Since the deck has 52 cards, there are 52 possible outcomes. The probability is therefore 4/52, which equals 1/13. What about the probability that the card will be a club? Since there are 13 clubs, the probability is 13/52, or 1/4. Let's say you have a bag with 20 cherries, 14 sweet and 6 sour. If you pick a cherry at random, what is the probability that it will be sweet? There are 20 possible cherries that could be picked, so the number of possible outcomes is 20. Of these 20 possible outcomes, 14 are favorable, or sweet, so the probability that the cherry will be sweet is 14/20, or 7/10. There is one potential complication, however. It must be assumed that the probability of picking any of the cherries is the same as the probability of picking any other. This wouldn't be true if, let us imagine, the sweet cherries are smaller than the sour ones. The sour cherries would come to hand more readily when you sampled from the bag. Let us keep in mind, therefore, that when we assess probabilities in terms of the ratio of favorable to all potential cases, we rely heavily on the assumption of equal probability for all outcomes.
Students, now we will talk about probability distribution. Probability distribution are fundamental concepts in statistics. They are used both on a theoretical level and a practical level,
ultimately in a much more rewarding way. So remember, this was the battle of the sexes. We know that there are 2 pure strategy Nash equilibria. There's the ballet-ballet equilibrium and the fight-fight equilibrium. And then there's also a mixed strategy Nash equilibrium where the players go to their more preferred form of entertainment with probability 2/3 and their less preferred form of entertainment with probability 1/3. So we've already calculated those equilibria in the past, but what if I were to change the Battle of the Sexes game in a very minute way? What if I were to turn these 2s into 4s, just like that? That doesn't change the ranked ordering of the player's outcomes. For example, the man still wants to go to the fight the most, along with player 2, and then he most wants to go to the ballet with player 2, and his least preferred outcome is still having this coordination failure where he's at the ballet and she's at the fight, or vice versa. So by changing those 2s to the 4s, we haven't changed the pure strategy Nash equilibria. Ballet is still in equilibrium. Fight is still in equilibrium. But we will change the probability distributions that actually form the mixed strategy Nash equilibrium. So if I gave you the solution to this game, you couldn't just tell me that the pure strategy, or rather the mixed strategy Nash equilibrium, is to go to your more preferred form of entertainment with probability 2/3 and go to your lesser preferred form of entertainment with probability 1/3. That's not going to carry over to this situation. Likewise, I can make another minor change to this game, move the 1s to 3s, and that's not going to change the pure strategy Nash equilibria, but it will change the calculation for the mixed strategy Nash equilibrium. So even if you'd solved the second game, that doesn't get you anywhere when you try to solve the third game. And again, I can make another slight modification, this time changing the 0s to 1s, and you're in the same situation as you were before. Even if you've solved the first 3 versions of this game, you still have to solve that mixed strategy Nash equilibrium again in this 4th game. And so that can be really frustrating if I'm giving you a lot of different versions of Battle of the Sexes, and you keep having to redo the math on the mixed strategy algorithm every single time. So it would be really neat and really convenient if instead of solving games with numbers, we could solve them with variables like this, where we're representing A as the most preferred outcome, B is the second most preferred outcome, and C is the least preferred outcome. And if we could solve the games in this generalized form, then we could then specifically plug in the numbers for, say, this 4th example and turn these A's into 4s, the B's into 3s, and the C's into 1s, and then solve for the mixed strategy Nash equilibrium by just plugging those letters into a fixed formula that we've already come up with.
Some practical uses of probability distribution are to calculate confidence intervals for parameters, to calculate critical regions for hypothesis tests. For univariate data, it is often useful to determine a reasonable distributional model for the data. Statistical intervals and hypothesis tests are often based on specific distributional assumption. Before computing an interval or test based on a distributional assumption, we need to verify that the assumption is justified for the given data set. The distribution does not need to be the best fitting distribution for the data, but an adequate enough model so that a statistical technique yields a valid conclusion. Simulation studies with random numbers generated from using a specific probability distribution are often needed. Probability distribution. Prerequisites to understand probability distribution. It is important to understand variables, random variables, and some notation. A variable is a symbol A, B, X, Y, etc. that can take on any of a specified set of values. When the value of a variable is the outcome of a statistical experiment, that variable is a random variable. A probability distribution is a table or an equation that links each outcome of a statistical experiment with its probability of occurrence. Cumulative probability distributions. A cumulative probability refers to the probability that the value of a random variable falls within a specified range. Uniform probability distribution. The simplest probability distribution occurs when all of the values of a random variable occur with equal probability. This probability distribution is called the uniform distribution. The complement of event E denoted by E dash and is a set of outcomes in S that are not included in event E.
Enable that to be a probability distribution function. Now we want the probability x is less than 15. How are we going to do that? We're going to label 15 on the graph, and we're going to shade everything that is less than 15. And certainly nothing goes below 10, since the function is only defined on the interval from 10 to 30. And the probability that x is less than 15 is going to be this area. So the question is, what is the area of that shaded rectangle? What we get as the probability x is less than 15 is the width of the shaded rectangle, 5, times the height of the shaded rectangle, 1/20th, to give us the probability that x is less than 15 is going to equal 1/4.
Here we will discuss how to calculate probabilities. This is a classical approach. Relative frequency approach. Probability of E may be interpreted as a relative frequency of the E over a long series of experiments. Law of large numbers. If an experiment is repeated again and again, the probability of an event obtained from the relative frequency approaches the actual or theoretical probability. Probabilities must be between 0 and 1 inclusive. A probability of 0 indicates impossibility. A probability of 1 indicates certainty. Rounding rule for probabilities P. Probabilities should be expressed as reduced fractions or rounded to 2 or 3 decimal places. When the probability of an event is an extremely small decimal, it is permissible to round the decimal to the first non-zero digit after the decimal point. Now we will discuss about the conditional probability and Bayes' theorem. The conditional probability of an event B is the probability that the event will occur given the knowledge that an event A has already occurred. The probability is written as the probability of B given A. In the case where events A and B are independent, where event A has no effect on probability of event B, the conditional probability of event B given event A is simply the probability of event B, that is probability B. If events A and B are not independent, then the probability of the intersection of A and B, the probability that both events occur, is as shown on the screen. From this definition, the probability of B given A is easily obtained by dividing by probability A. This is shown at your screen. Let's describe Bayes' theorem. Bayes' theorem describes a relationship that exists within an array of simple and conditional probabilities. Bayes' formula is as shown on the screen.
Hello, David Harper of the Bionic Turtle with a brief tutorial on Bayes' theorem or Bayes' formula, a basic idea in probability that turns out to have profound implication in practice. To illustrate it, consider my friend here, the stick figure character, facing a decision among 3 doors. But first consider he has no prior information. He is unknowing. He is ignorant. This is an unconditional probability, really. Now, add some prior information. Assume that he knows he comes into possession of some information to indicate that one door is more promising and another door is more dangerous. This addition of new information rationally should affect his judgment and his probabilities. So this is really what Bayes' theorem is about. It's about the introduction of new information to adjust the probabilities. So mathematically, it looks like this, where we say the probability of G given that U occurs is equal to this. So this right here is a conditional probability because we're interested in the probability that G will occur conditional on the fact that U has already occurred. And it equals this. In the numerator, we have a joint probability. See, the probability of G, if that occurs, it gets multiplied by the probability of U given that G occurs. So in fact, what we have here in the numerator is a joint probability that both U and G occur divided by the probability of U. Okay, but if that seemed confusing, I'll show you a graphic. And just remember, this is a conditional probability. What we're doing is we're adding new information. Now that we know, if we know that U is going to occur, what is our new conditional probability that G will occur? The denominator breaks out into this following way, but I'll go to a graphic to show you how this works.
Now in the end, let us summarize what we have learned in this lecture. Probability theory deals with situation in which there is an element of randomness or chance. The mathematical theory of probability arose in consideration of games of chance, but is now widely used in far more practical and applied situations. Probability is a branch of mathematics that studies the possible outcomes of given events together with the outcomes' relative likelihoods and distribution. The analysis of events governed by probability is called statistics. Bayesians treat probability more subjectively as a statistical procedure that endeavors to estimate parameters of an underlying distribution based on the observed distribution. A properly normalized function that assigns a probability density to each possible outcome within some interval is called a probability density function, and its cumulative value is called a distribution function. Probability distribution are a fundamental concept in statistics. A cumulative probability refers to the probability that the value of a random variable falls within a specified range. The conditional probability of an event B is the probability that the event will occur given the knowledge that an event A has already occurred. Bayes' theorem describes a relationship that exists within an array of simple and conditional probabilities.